So in this video we are going to see a snapshot implementation. Here we are going to present a log-free implementation of a snapshot object, and we're going to try to see if it is correct or not. So here we can see the implementation of this snapshot object. So here we have an array of n atomic read and write registers, and then here we have the update operation, and here we have the scan operation. Now the update operation simply writes value v to position I of this array, where I corresponds to the identifier of the process running the update operation. And then here we have the scan operation. The scan operation simply calls a collect operation on this array, stores the result in AA, and then it executes the following loop. So then it collects everything that is stored in this array, and if what it read here and what it reads here is the same, it returns. Otherwise, it stores what it just read to AA, and then it repeats the loop. Now let's see how collect works. Collect simply goes through this array that is being provided as a parameter, stores all the elements in this temporary array, and then returns TMP. Now, as we can see, this is not a wait-free implementation. Why? Because this while loop here might never terminate. Because this while loop here might never terminate if there are processes that are performing updates in the array. The question though is the snapshot object implementation that is being shown here, so is this a correct log-free and linearizable implementation? So in this problem, we have to show if we believe that this is correct, we have to prove it. I mean, if it is correct, we have to prove it, present a proof. Otherwise, if this is not a correct log-free implementation and linearizable implementation of a snapshot object, a counterexample would suffice. So a good way to think about those problems is that since you have already seen such a snapshot object in class, is kind of try to think about what are the differences. Naturally, this is a log-free implementation, it's much simpler, but what it is missing the timestamp. So it is missing this notion of a timestamp. And kind of this can hint to the fact that this is probably an incorrect implementation of a snapshot object. It's one that is not atomic. And in order to prove that it is not atomic, we can try to look up for a counterexample. So how can we do this? So as you probably guessed, the algorithm is not linearizable. And here's an example where we show that atomicity could be violated. So consider this scenario where we have three processes. Process P1 is performing this long-lived scan, and then process P2 and P3 perform update operations. Now furthermore, consider that the initial state of our array is 0, 0, 0. Then we have process P2 performing update with value 1, then with value 0, 3, 0, and 3. And then process P3 first performs an update with value 2, then with update 0, value 2, value 0, and then value 2 again. So if we take, let's say, a line here, what is the state of our array? It's 0, 1, 0. If we take a line here, what is the state? It's 0, 1, 2. And then if we keep doing this here, let's say, what would be the state? It would be 0, 0, 2. And here it would be 0, 3, 2. And then after this update by process P3, the state would be 0, 3, 0. And then after this update by process P3, it would be 0, 3, 2 again. And then here it will be 0, 0, 2. And then after this point, it would be 0, 3, 2. And then after this point, it would be 0, 3, 0. And at the end, it would be 0, 3, 2. So here we have seen after its update what is the state of of this array, and we see it's never 0, 0, 0. So it's never 0, 0, 0. Naturally, if we were to take the state, let's say, kind of during the execution of some update operation, again, it would never be 0, 0, 0. Okay, let's clean this a bit. This means that if this scan operation was to return 0, 0, 0, atomicity would be violated. Is this possible? And indeed, we can see that it is possible. Recall that the scan operation reads this array one element after the other. So it could be here that it reads register of 1, which is 0, and then at this point in time it reads register 2, which is 0, and then at this point in time it reads register 3, which is again 0. So the first collect would just return 0, 0, 0. And then the scan has to perform a second collect. So in the second collect, after this point, it will, let's say, read register 1, which is 0, and it would also read register 2, which is again 0. And then after this point here, it would read register 3, which is again 0. So the second collect would also return 0, 0, 0. Which means what? It means that this scan operation will return this here. But of course, such a result violates linearizability. So a good way to prepare for this course and to actually get a much better understanding of the algorithms that are present in this course is to kind of think about the algorithms. If I change this, would it still be correct? Can I find a counterexample? And so on and so forth. Why is the algorithm correct? Is the timestamp really needed? In this case, we saw that it is, yes.